All right, so go ahead and get out your optimization packet, and we are going to flip to page 4. And today we're going to finish up the classwork together. And then your assignment will be to finish the packet. All right, so on number 5, the size of a population of bacteria measured in thousands introduced to a food grows according to the formula P of T equals 6,000 T over 600 plus T squared, where T is measured in days. Determine what day the bacteria population is at a maximum and find the maximum size of the population. So this is one where we're given the formula to maximize, so we don't have to worry about constraints. We just need to start going through the process of finding the derivative. Now, this is not going to be an easy one to find the derivative, because if you guys notice, we're going to have to do the quotient rule, which is something we haven't done in a long time. I hope you guys remember it. But remember, it's low, and then D high minus high, D low, over low squared. Okay, and then we have quite a bit to simplify down here. Now that denominator, we don't want to multiply out or anything, or just leave it like it is. Oh, that should have been T squared. Okay, so we want to find a critical number. So when this is 0 or when this is undefined, for it to be undefined, that denominator would need to be 0, but there's not a real number I can put in for T, and at square, add to 60 square and get 0. So we don't have to worry about the denominator. So we want to find where the numerator is equal to 0 for your critical numbers. All right, we'll do the square root, and we get about 7.746 for how long it takes. That's how many days. Now, we want to know if this is a maximum or a minimum, or maybe neither. I don't want to find the second derivative of that, because that's just more work than what I want to do. So instead, let's just use the first derivative test. All right, so we'll find P prime of 7, and we'll find P prime of 8. And then what I did to do it, and I don't want to waste time plugging in, is I just plugged 7 in, and I got a positive, and then I plugged negative into the derivative, and I got a negative. So whenever the first derivative changes from positive to negative, it creates a relative maximum there. And so to answer this question, it says on what day, right? Determine the day. So the day would actually be the 7th day. max occurs, or during the 7th day, on it or during it. And that max is P of 7.746. And when you plug it in, you get 387.298, and that is measured in thousands. So we'll just go ahead and say 387,298 bacteria. All right. For number 6, we're going to find the point on the graph of the function that is closest to the given point. So this is a square root function that's shifted over to the right, and we want to find the point on it that is closest to the point 60. So I'm going to just do a little sketch. It's not necessary to do the sketch to do this problem, but like this was shifted over to. All right, the point 60 would be like right here. So we want to know what's the closest point to this point, from that graph to this point is what we're looking for. And so to find the shortest distance between 2 points, we have to do the distance formula. It might have been a while since you've thought about the distance formula, but you subtract the x and square that, and then plus subtract the y's and square that. Okay, so we have everything we need actually to do this. So x is 6 is an x and 0 is a y, and then this square root of x squared minus 2 is also a y. So I'm just going to plug those things in. All right, and then we'll simplify it down. So square x minus 6. All right, and now when you subtract 0, it obviously goes away. And then when you square the square root, you're just left with what's underneath. Okay, so that is the equation that we want to minimize. Now, I don't really want to use that equation because it's the square root of a polynomial. So we can kind of do a shortcut because this thing is going to be the smallest when the radicand is also the smallest. So we can just minimize the radicand. So because D will be smallest when the radicand is smallest, we can minimize the radicand. Now, we don't want to call it D, and we don't want to call it F, so let's just call it G. Okay, so then we can find the derivative. We can find the critical numbers. All right, and then just to double check that that's a minimum, we can find the second derivative. And we get 2, well, because this function, the g function, is always concave up because it's a parabola open upward. So that's always positive. So the critical number on a concave up parabola is going to be a minimum. because it's positive. So x is the value of the x coordinate of the point, and we want to find the y coordinate, so we can do that just by plugging our x in here. So 11 halves minus 4 halves is going to be 7 halves. So that's your point, 11 halves, and then the square root of 7 halves. So that should be the one that should be where on that radical function is the closest to the point 60. Okay, let's look at a couple more. So number 7, these are pretty common in optimization problems too. So a rectangular page is to contain 24 square inches of prints. The margins at the top and bottom are to be 1.5 inches, and the margins to the left and right are to be 1 inch. What should the dimensions of the page be so the least amount of paper is used? Okay, so let's just do a diagram real quick. So this is the whole page, and then this is the printed stuff. And the printed stuff needs to fill in 24 square inches. All right, I also know that on the left and right, I have 1 inch margins. And on the top and bottom, I have 1.5 inch margins. Okay, and then I'll call this length X and this length Y. All right. So I want to minimize the area of the page. So the area of this rectangle, this side should be X plus 2. And the other side should be Y plus 3. That's the length of the page times the width of the page. All right. So that's a little bit of an issue because we have X and Y. So we are going to have some kind of constraint to help us with that. And our constraint deals with the inside print. So the X times the Y, the area of the inside should be 24. All right, so that means we need to solve it for either X or Y. When I did it before, I solved it for X. It honestly doesn't matter. So when I go back up in my area formula, I'm going to replace X with 24 over Y. And I definitely want to multiply that together before I try to find the derivative. So that's what you should get when you multiply it out. Just double distributing. All right, and then I'm ready to find the derivative. This is another one that we've been talking about whenever you have a number over a variable. So remember, we just change the sign of it, and then if that variable is only y, no exponent, we make it y squared. All right, and then the derivative of 2y is just going to be 2, and the derivative of 30 is 0. Okay, and let's see if you guys need to see all that at one time. Then we want to find the critical numbers. So we'll set this equal to 0. So we're going to get that y is 6. And then just to make sure that this is going to be a minimum, not a maximum, let's do the second derivative real quick. All right. So this is another one. We can do a shortcut, but it's a little more challenging because we have that exponent on the bottom. So remember, we do change the sign. So it was negative, we change it to positive. Then we multiply by that 2. And then it's y to the third down there. All right, and we don't necessarily even need to know what 2 times 72 is to figure out what we want. We just need to be able to plug in the critical number and know if we get a positive or negative. So when we put in 6 for y, it's a positive divided by a positive, which is a positive, which means that this is going to be a minimum. Okay, so let's answer the question. What are the dimensions of the page? So the dimensions of the box are 4 by 6. But don't forget the page has additional margins. I think it's the way this is worded, we're talking about the whole page. So we remember we have to add those margins of 1 and 1.5. So it looks like it's going to be 6 by 9 inches, right? So it's just the x plus the 2 and the y plus the 3. All right, and then for the last one, look at it. A box question. So we have a container with a rectangular base, rectangular sides, and no top is to have a volume of 2 cubic meters. The width of the base is to be 1 meter. When cut to size, the material costs $10 per square meter for the base and $5 per square meter for the sides. What is the cost of the least expensive container? And we're going to verify it's a minimum and not a maximum, which we've been doing that on all of these problems anyway. Okay, so let's draw a box. I'm not super awesome at drawing boxes. Wait, terrible. Okay, so we know the width has to be 1, so we'll go ahead and say that that's 1 meter. So we'll say that, well, this is the length and this is the height. Okay, this one's got a lot going on. So let's just start with the $10 surface. So that's the base. And so our base is going to be the length times the 1 meter. or just L. Okay, and then we'll look at the $5 surface. So we have to break this down into the front and back. And the sides. So looking at the front is going to be the length times the height. That area is. And the back should match up. So we have 2 of those. So 2 for her. 2 length times heights. All right, and then the sides are going to be the height times 1. All right, because this would be a height also. So the height times 1. And we have 2 of those. Or just 2H. All right, so let's look at the cost. This is kind of like the CAM problem we started this whole thing off with. Okay, so $10 times the area for that surface, and then $5 times each of these. All right, I'm going to simplify that down because when I did this the first time, I kept just messing up. I don't know. I was in a weird mood, I guess. Okay, so we have a little bit of an issue because we have L's and H's. So I would need to go back and use a constraint so I can just solve for one or the other. So let's find what we can use. The only thing we can use is that the volume is to be 2 cubic meters. So that means when I do the length times the width times the height, that's going to be 2. All right, so I already know my width is 1. And then I can solve for either L or H. Let's just solve for H. So we can replace, that looks weird, we can replace H with 2 divided by L. So let's do that for these 2 H's. And then we can call it C. Well, we could call it C before, but anyway. So in the place of H, we'll do 2 over L. And then we'll do it again over here. Let me just clean it up a little bit. Those L's cancel out. Keep wanting to put an equal sign. Okay, we're good. All right, so now we want to do the derivative. Derivative of 20 is just 0. And then here we can do our little trick we've been doing where we change the sign, and then it's 20 over L squared. Okay. Now we want to find where this is 0. So I'm just going to keep going down. So we'll set it equal to 0. So L needs to be the square root of 2. Sorry, I went down to the other page. All right, to verify that that is a minimum, I'm going to come over and find the second derivative. All right, so because my L has a power this time, I'm going to multiply by it. So I'm going to change the sign from negative to positive, multiply by my power, and then it becomes a cubic down there. All right, then when I put in the square root of 2, I get a positive divided by positive is a positive, so that means this critical number is a relative minimum. All right, and then it asks, what is the cost of the least expensive container? So I just need to go back up and put the square root of 2 in for my L in this equation right here. And I get that is $48.24. All right, so I want you guys to finish up the packet today, and then tomorrow should be Friday, so you'll have a Friday assignment. So make sure you get the notes and the assignment for that before you leave.